So last time we talked about using those BCA tables and the ice tables to figure out our pH after adding a little bit of acid or base to a buffer. And we saw that when we did that, the buffer resisted that change in pH, and so the pH of that solution didn't change a whole lot, even when we added a little bit of that acid or base. Now, moving on to slide 8, if we know the Ka, our concentration of our acid and the concentration of its conjugate base, or if we know the base and its concentration of conjugate acid, then we can use the Henderson-Hasselbach equation to find our pH. This is usually a lot easier method than going through the whole process of writing out an ice table. Okay, but in order to use it, you have to know the Ka, you have to know the concentration of the acid and the concentration of the base, or the base and conjugate acid respectively, depending on the problem. Okay, now our Henderson-Hasselbach equation is that the pH is equal to the pKa plus the log base 10 of the concentration of base over our concentration of acid. So in the case where we knew the Ka, the acid, and conjugate base, it would be the conjugate base concentration over our acid. Okay, so a lot of times people often write it as pH is equal to pKa plus the log of the concentration of A minus, which is kind of like your base, right? The one without the extra proton. And that's going to be over your concentration of HA, which is the one with the extra proton. Okay? A lot of people write it that way. Either way is fine for me. Okay? Now, let's do an example of this. Let's say that a buffered solution contains 0.25 molar ammonia and 0.40 molar ammonium chloride. If the Kb is equal to 1.8 times 10 to the negative fifth, then what is our pH of that solution? Now, the way that we would solve these problems is first we're going to identify our initial concentrations. Okay, we know that ammonium chloride has the extra proton, so it's going to be our HA species. We know that our ammonia does not have that extra proton, so it is our conjugate base, or our A minus species. Okay, so that makes our HA concentration equal to 0.4 and our A minus concentration equal to 0.25. Right? Then we're going to be able to calculate our Ka from Kb. Okay, and we have to do this because we need the pKa for our equation. Okay, and we were given the Kb in our problem statement. Okay, so to calculate your Ka from Kb, remember that Kw is equal to Ka times Kb. Now, Ka is equal to Kw divided by Kb, using algebra to rearrange this. We know that Kw is a constant, okay, and it's going to be 10 to the minus 14 always. So I would have that memorized because it's going to be useful over the next several days. And then we're going to divide our Kw by our Kb, which from our problem statement was 1.8 times 10 to the negative fifth, and that gave us a Ka of 5.56 times 10 to the negative 10. Once we have our Ka, then we need to calculate our pKa. Remember that P, right, the potence or whatever, okay, that's just the power of the Ka. And we found our power by taking negative log base 10 of whatever we put inside, which in this case is our Ka. Okay, so it's the negative log base 10 of our Ka, so negative log of 5.56 times 10 to the negative fifth is 9.25. So we've got our pKa. Now that we've got that, we can use our Henderson-Hasselbach equation, where we had our pH was equal to our pKa plus the log base 10 of our ratio of our base over our acid. Okay, we plug in our pKa, which we found to be 9.25, and then we added on the log of our concentration of our A minus. Remember that our A minus was the NH3, which was 0.25, and we put that over our HA, right, our acid species, which was the NH4 with the extra proton chloride, and then 0.24 was that concentration. Okay, plugging in all of those values, we get 9.5 as our pH. Notice this was a lot shorter than doing an ice table, okay, and all we had to do was figure out what our acid and base species were, figure out our Ka, plug it all into that equation, and we were good to go. All right? Now, we can also use the Henderson-Hasselbach equation to determine the grams or moles or whatever of a substance that we need to add to a solution in order to make a buffer with a specific pH. So we can use the Henderson-Hasselbach equation to make any pH buffer we want. Okay? Now, to walk you through how to do that, let's take a look at the example on slide 9, which says that, let's say we want to calculate the mass of sodium acetate that is needed in 500 milliliters of a 2 molar solution of acetic acid in order to form a buffer that has a pH of 5. All right? The Ka for acetic acid is 1.8 times 10 to the negative fifth. All right? Now, to start this problem, we know that it's going to be, since we're trying to make a buffer, we want to form a buffer with a specific pH, all right? If that's the type of problem, then we know we're going to use the Henderson-Hasselbach equation, all right? So we've got a Henderson-Hasselbach equation, and what is that? That's going to be our pH is equal to the pKa plus our log base 10 of our concentration of the base species over our acid species, right? And so once we have that, right, we know that we need to find the pieces to plug into this, okay? We already know our pH, right? We know how to get our pKa because we have our Ka, all right? And we have our concentration of our H-acetic, which is going to be our acid concentration. So the only thing that we don't know in that expression is our A- concentration. So we're going to need to solve for our A- concentration. All right? Now, the way that we do this is we're going to plug in all the values that we know first. Okay, so we have our pH. Our pH was 5. And that would be equal to our pKa, which is the negative log base 10 of our Ka, which is 1.8 times 10 to the negative fifth. And then we're going to add the log of our concentration in A- over our concentration for HA, which was 0.200 molar. Okay? Now, at this point, let's do some simplification, right? And I'm going to pull this log over to the other side. So I've got 5.00 plus the log base 10 of the 1.8 times 10 to the negative fifth is equal to the log of our concentration in A- over 0.200 molar. Okay? Now, at this point, let's plug that into our calculators and see what we get. We get that this is equal to a 4.7, or this is equal to a negative 4.74, okay? So when we add those two together, we get a 0.26, okay? And then that's equal to our log of our concentration in A- over 0.200 molar, okay? Now remember, this is the log base 10. So if we want to take this out of the log, we're going to raise both sides, okay, using the base 10. So we have 10 to the 0.26 is equal to 10 to the log base 10 of our concentration in A- over 0.200 molars. Don't forget how to do logarithms. When we have 10 raised to the log of the same base, then what we get is everything inside. So this ends up being equal to our concentration in A- over 0.200 molar. Okay? Now, if you ever forget, just remember you take 10 to the right, or you take 10 to what you have over here, and then you get whatever's inside the log on the other side. Okay? Now, that means that on the Left-hand side here, we have 1.8197, and that's equal to our concentration in A minus over 0.200 molar. So if we want our concentration in A minus, that is equal to 1.8197 times 0.200 molar, which gives us 0.3639 molar. All right. Now, it asked us for the mass of the sodium acetate. Okay. And this is just the concentration of our acetate ion. Okay. Now, acetate ion, all right, is C2H3O2 minus. You guys should have that memorized from your polyatomics. Okay. So basically, it's the concentration of that. Okay. Now, we have 500 milliliters of the solution, okay? So I'm going to convert that into liters, and I'm going to use that with my molarity to get my number of moles, okay? So I have 0.500 liters of the solution, and I'm going to multiply that by my concentration, which was the 0.3639 moles per liter, okay? And then I know that 1 mole of my acetate ion is equal to 82 grams, okay, because it's 82 grams per mole, which gives me 14.9 grams of the, oh, and sorry, this isn't the acetate ion, this is the sodium acetate. All right, in here we should probably have a 1 mole to 1 mole ratio, because we know that sodium has a +1 charge and acetate has a -1 charge, so it's 1 to 1 mole ratio. So then we end up with 14.9 grams of our sodium acetate. All right, so that means that if we added 14.9 grams to this buffer solution, or to this solution of the acetic acid, we would get a buffer that has a pH of 5. If we adjusted that amount of the sodium acetate, we would end up with a pH of a different value for this particular buffer. Okay, that allows us to adjust our pH very quickly and easily without having to do an ice table or a lot of that other math. Okay, again, we can only do this, we can only use our Henderson-Hasselbach equation if we have our Ka, our concentration of our acid, and its conjugate base, or a base and its conjugate acid. All right. Now, the next thing that I sort of want to talk about, and it's more conceptual than anything, okay, is something called your buffering capacity. So, on slide 10, all right, we're going to introduce this idea, which is basically how much a buffer can absorb into its solution and not change its pH a whole lot. Okay, so essentially this represents the amount of H plus or OH minus ions that the buffer can absorb without changing the pH significantly. Okay? Now, let's say that we use our Henderson-Hasselbach equation, right? And we say, oh, well, I found my pH is equal to pKa plus the log of my base over my acid okay? Let's say that we found our pH, okay? Our best buffering region is going to be the pH plus or minus 1 value in pH, okay? So that means that our buffering capacity, let's say we had that our pH was equal to the negative log of 1.8 times 10 to the negative fifth, right? That's for acetic acid. Let's say we got our pH was equal to 4.74, okay? If we found that our value was 4.74, then that means that our buffering capacity is going to be this pH, the 4.74, plus or minus 1 value in pH, which is going to be anywhere from 3.74 all the way up to 5.74, okay? So that would be your buffer range for this acid in that region, okay? So again, it's not very hard. You just find your pH, then you add and subtract 1 value from that pH. And that's going to be your best buffering capacity. Right? Now, one last thing that I wanted to go over with y'all in this video is this idea of titrations. And the reason that I wanted to touch on titrations is because we're going to be spending the next several videos going through the different types. Okay, so slide 11, titrations. All right, so basically for a titration, we're going to have 3 main types. We're going to have a strong acid and a strong base. Okay, this is called SASB, right? Strong acid, strong base. We're going to have a weak acid and a strong base. Write that out. A weak acid and a strong base. And then we're going to have a strong acid and a weak base. Okay? Now, what we do in a titration is we have the burette, the long tube, right? It's got little markings. And a burette tells you the amount that you added. So the readings on it start off low at 0 and then increase for the amount that you've added, okay? So there's usually a little valve down here, and then it allows you to drip into a sample to analyze your pH at the bottom, okay? So you always are going to put a species of a known concentration into your burette. The one that goes down here is going to have an unknown, whether that be your constant, and it should be an unknown concentration, okay, or pH or something like that. Now, in the burette, that component is called your titrant, okay? And the one that is in the flask is called your analyte, okay? Sometimes people use different names. I'm probably going to use these for the most part in this class, okay? Now, when you run the titration, let's say that we are running a titration with an acid down here, and we put our base as our titrant. Now, when we do this, we're going to be tracking our pH. So a lot of times we'll put something called an indicator. And that indicator is going to change color when the pH changes from basic to acidic, or from acidic to basic in this case, right? It starts out acidic, so there should be a color change as we go to basic if we've added our indicator. All right? Now, since we're starting out acidic, let's plot our pH versus the volume of base added. Okay? That means that since this is an acid, our pH is going to start out low. Okay? And we're gradually going to go up in pH a little bit, and then at some point we will reach equivalence and it will become basic. So this would be your equivalence point. Actually, I won't define that yet, okay? But as we're adding it, okay, let's say that our solution started out acidic and we've added phenolphthalein. Now, phenolphthalein is a particular kind of indicator that will turn it pink, okay, as we go along. And so, if our flask at the beginning started out with a clear solution, the more that we've added, once we reach our equivalence point, it will be a very faint pink, okay? And then once we pass the equivalence point and it becomes basic, all right, we will have over titrated and it will be a very deep red, okay? Again, I tried to draw this as pink, right? The point at the equivalence, or the color at the equivalence point when we're doing the titration, okay, is going to tell us whether we reach that point or not. Now, in this case, right, we can use this value to figure out our concentrations and other properties related to how many moles that we've added. And I'll talk a lot more about this in our next several videos, but I wanted to kind of give you an introduction to sort of what we're doing with our titrations, okay? So again, as we're adding more and more base to our acid, at some point, the moles of acid and the moles of base are going to cancel each other out. So if we keep adding more and more base, our new solution is going to be basic. So before this point, it's acidic. At this point, it's neutral. And then after that point, it's basic. Again, because we start out with a low pH, acid up to neutral, and then beyond would be the basic. Now, of course, if we were analyzing a base, okay, and using an acid, so if we had an acid here and we wanted to analyze a particular unknown sample of base, okay, our pH would start out high because it's a base. It would gradually decrease, go past, and then we would end up, as we continue to add acid, become acidic in solution, okay? And we would use a different type of indicator in that case, okay? So that concludes our introduction to titrations, and then we will start on some examples in our next several videos.